Hello and welcome to Disseminate, the podcast bringing you the latest computer science research. I'm your host, Jack Wardby. Today we're recording from ACM Sigmod Pods in sunny Philadelphia. I'm delighted to say I'm joined by Draco Zhu.
Hi, I'm Draco.
From the University of Rochester, and today we'll be talking about his paper TSUBASA, Climate Network Construction on Historical and Real-Time Data. Thank you for joining us on the show.
Thank you for inviting me.
Let's dive straight in. Can you first introduce your work and describe the problem that your paper is aiming to solve and the motivation for doing so?
Okay, so the TSUBASA, the goal of TSUBASA is to provide climate scientists a way to construct the climate network from the time series. And here, the climate network could be there are two basic concepts in a network. The first is the nodes, and the second is the edge. The nodes, you could just imagine, is like a city. So, for example, we have some people, they are recording the temperature of, for example, the Philadelphia. So, what's the temperature like in this second? And every 5 seconds, so they will record like a new one. So, it's like an updating one. And so, everybody, in every city, is doing that. So, you can imagine maybe there are 1,000 cities in the world. So you have 1,000 people, they are recording and they update it every 5 seconds. And then, so that's the nodes. So the nodes are all the cities on the world. And then you want to know the age. So what's the age? The age could be the degree of the correlation, so between the behaviors of this time series. So for example, you want to know whether the weather here in Philadelphia is correlated with the weather in New York City. So as a climate scientist, you might want to know these kind of things. And then we can compute a measurement called the Pearson correlation to measure the degree of the correlation of these time series. And then you could compute that for Philadelphia and the New York City, and you could compute it for every pair of the cities. And for example, we have 1,000 cities, then you could have 1,000 times 1,000 pairs. And then you could get a matrix. So the matrix, so nothing special. So just so for each point in this matrix, it tells you a correlation between every pair. Mm-hmm. And so that could be a large network if you have enough nodes. And the key point is that if you want to update for every 5 seconds, because the temperature will update it. And maybe your computer is not good enough to compute it in 5 minutes or in 5 seconds or in 1 second. So you need a fast way to compute that one. And the researchers in this area, so they have proposed some ways to compute it. And so before I address these these problems, so they can do it in a very good way. But they can get an accuracy above 90%, but it's still not exact the value. And if you want to get exact the value, because in some certain types of the research, the exact correlation value is really important. And if you want to get the exact value, so can we have a way to do that? So can we find a method to extract the value of the correlation? So that's the main goal of this research and motivation. Yeah.
Fantastic.
Yeah. Mm-hmm.
That's brilliant. So knowing that, what is the solution you developed in your research? How did you tackle this problem?
Okay. So the main idea is that you want to have something prepared. So there's a basic concept that, so when we're talking about the correlation, so we have a time period that you're talking about. So you want to know whether the temperature in the Philadelphia is correlated with the weather in the New York City, but you need to specify a time range for it. So for example, in the last 1 day or in the last 10 days or in the last 1 year or something like that.
Yeah.
And then in our research, there's a definition to describe these things. It's called a curve window. Okay. And then the curve window might be small or might be large. And each time you update this one, so only a small amount of the data will be changed. For example, you have so you want to know the correlation in the last 5 days, and then after 5 minutes, it's updated. So only 1 point is updated, and you want to update this 1 point. So the key idea is that you want to summarize information for the last 4 days plus blah, 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 and you want to add information of one data point. So here are 2 steps. The first one is that you want to summarize information for the past few days. And then you want to find a way to combine the information from the new coming ones with the ones that we with the ones that we prepared. So when we're summarizing the information for the past data, so that's why we need a concept called basic windows. So basically you need to cut these time series into small groups. So you can imagine that we can group the data point in 1 hour to a small window, and that's called a basic window. And then for example, for yesterday, so we have so we can have the 24 basic windows, and then you want to get some statistics from these basic windows. You don't want just to keep the raw data. So the raw data, there could be hundreds of data there, but you might only want to keep 1, 2, 3, 3 data points. And from these, you can get the correlation. And these statistics, so what we use is the correlation between these basic windows and their mean and their standard deviation. They are easy to compute. And so I think that's the main point.
Fantastic. What's the improvement of your solution over the existing work? And obviously you alluded to before that yours is obviously as an exact solution, whereas other ones are approximations of correlation.
Okay, yeah. So as I mentioned, most of the advantage or the improvement is that we can achieve the exact one, which is 100%. And the second one is that in the previous work, on the usability of the curve window is really limited. So let me explain this. So for example, the basic window concept is used in the previous works. So when you want to get the correlation, so for example, so maybe you want to know the correlation between the 3:30 to the 5:30, and if the basic window are the 3 to 4 and 4 to 5. You can never ask the algorithms or the system these questions, because the starting point is the 3:30 and it's not aligned with the 3. So it requires that the size of the curve window is divisible by the size of the basic window. So that's the first requirement of the previous the algorithms. And the second one is the starting point and the ending point of the curve window should be aligned with the starting point and ending point of the basic windows. And that's the second limitation. And in our solution, we don't have these things. So you can query from any point. And so that's one easiest sense, because because the size of the basic windows is really important. And if you just limited the user that you can only start from this point and from that point, that's really not efficient in the climate research, because they provide you a way to get more possibility to do the research, I guess. Yeah.
Okay, awesome, great. So so I'm imagining that you have a toolkit that you can use that is it available online on GitHub that people can go and use to use your model, use your techniques?
Yeah. So besides the codes that we provide for this paper, we also implemented it as a Python library. So
okay, nice.
And it's called TSUBASA. Actually, so Jinshu, who is sitting just beside me, so he is the main author of this library. And so in this library, we implemented all the algorithms that we mentioned in this paper, and we also implement some further functions that is useful in the climate research. For example, the sliding window one or some other functions. And so in that library, so you can just to search the TSUBASA on the GitHub, TSUBASA, and you can also download it from the Pearson. And there's a document there. You can follow the document, and in the Python code or in your Jupyter notebook, you can just use the functions that we have already prepared for you, and you can just load the data set and do your research.
That's brilliant. We'll link to the library in the show notes and all the relevant information, so people can go and find that if they're interested. Awesome. So the next question I have is, what is the most interesting or unexpected or challenging lesson that you learned while working on this topic?
So like the most challenging one.
Yeah.
Right? I think the challenge is that it's like a trade-off. So like in the research, we talk about like the space complexity and the time complexity. So basically these two ideas is that, so I mentioned that we need to summarize some information from time series. And so here we only keep like 3 statistics. But if we keep more, we might be more efficient in the query time, which is generating a network. But if the scratch and the summarization is too much, then maybe you need a larger computer to store these things. You need a large the server to do these things. And if you store like too few things, then you need more time to do the query. So since we really want these algorithms and the library to be useful in the research, so we really need to find a balance between these kind of things. And I think that's like a key challenge in this research.
My next question is, what do you have plan for future research in this area? What's the next steps? Where do you go from here?
Okay. So as mentioned that here we need like the trade-offs between the time and the space, and we can do some improvement for that. For example, we can minimize the space complexity, and for time complexity we can also do some things. So we have like another idea is that we first to prune in some pairs of the time series. So you know like which pair of these time series could have a high correlation, and you pick them, and then you check them. So like the picking step is not too expensive, so you can pick the candidates and then you choose from the candidates. So here we just like compute every pair of these basic windows, and it's not like smart enough. So the idea is that we pick all the candidates and we choose from the candidates. So that's the main idea for the next step. And here, so you know, like the paper, so after we submit the paper, so there has like several months, and we also worked on like another algorithms, which is the sliding one. So you can imagine that if in the historical data, so for example, you want to know like the correlation for the 2020 to 2021, 2022, and so that's called like the lag sliding. So the size of the window is unchanged, but the starting point and end point is changed. And in the sliding, we have like an improved algorithms, which is like you make some prediction for the next step. So, and in that way, you might not need to compute that one, but you can get the result. So that's like 2 things that we want to do. And also, so this kind of the correlation-based network is common in a lot of like areas. It's not only important in the climate research. For example, here I mentioned like the nodes could be a city, but nodes could also like be a brain region, right? So like the neuroscientists, they also want to know like the correlations between the brain regions. And in neuroscience, that's called the connectivity, or it's called like the functional connectivity. They want to know, so when you are looking at something, when you are thinking of something, so maybe 2 parts of your brain are correlated. And maybe this kind of correlation will tell us that how the brain, so how it processes information, how they send this information. And from these neuroimaging things, we can do the single neural record to have some more neurophysiology things or something like that. But the point here is that this kind of correlation-based network is common in a lot of other regions. But another important thing is that in each regions, the research field, like the point is different. So here in the climate research, the time resolution is really important. For example, the temperature will be updated like in 1 second, in 5 seconds. So we need to achieve that kind of like the speed. But maybe, for example, in the neuroscience, it's not updated so quick. Maybe like we need to achieve like a high accuracy or like low overheaded or like the fast speed. So I don't know. So I mean, So for different kind of fields, so they have like different kind of the requirement. And if we really want to extend it to the other domains, and for example, we want to write a library for the scientists in other domains, then we need to know like their requirements. So and then we do some improvement to it. Yeah, I think
awesome. That's great. So that will allow you to explore other areas of these trade-offs you were talking about.
Yeah.
Which, that's great. What are the other application areas? So you mentioned obviously there's climate, there's neuroscience. What's the other common application areas for this work?
For example, in finance, I guess, so like the stock market. So some kind of the financial research, so they want to know the correlation between some stocks and other like financial time series. Or like, so there is like one called like the Bitcoin. Bitcoin. You want to know the correlation, and in that one, it's updated like really frequently, know. And I guess it's more than 1 second. So I mean like, so you can see like this kind of research, or you can see also like in the physics. So like they have like some experimental physics. So they are doing the experiment. So you have like some sensors. Like you putting them in the lab and you want to know the correlation matrix or something like that.
Okay, brilliant. Well, fantastic. We'll end it there.
Okay.
Thank you so much, Draco, for coming on the show. If you're interested in knowing more about Draco's work, then the links to the paper and all of the relevant libraries and everything will be put in the show notes. So thank you and see you next time.